Now, the way that I want to look at this, at least from the intuitive point of view, is not in the textbook. So I want to go back to an older idea. And here I am on the Wikipedia page for Leibniz. Leibniz is one of the people who first started to write about differential calculus in the late 1600s. So he published around 1682. He has some personal diaries and stuff that talk about his calculations, maybe like 1675-ish. And Leibniz wasn't afraid to talk about infinitely small quantities. So I want to be very careful here that what I'm going to talk about are not real numbers in the same way that positive infinity, negative infinity are not real numbers. But I find they make a very intuitive picture for trying to find slope of functions which aren't lines. So this idea, I'm showing my slides here, this idea is called a differential. It's where we get the name for differential calculus. Now, the idea is that there's some variable that I'm working with, maybe more than one. In mathematics, we usually use single letter names, usually taken from the Latin alphabet, sometimes the Greek alphabet. And every variable I work with, whether it's an X or a Y or a Z or a U or a V or a W or a T, and any of those letters is fine, each one of them has a corresponding differential. And the differential represents an infinitely small change in that variable. So this is what infinitesimal means, the way that infinity means larger than all real numbers. And that's not a real number, right? You can't be larger than everything if you are included in the everything that you're supposed to be larger than. Don't think about it too hard. Infinitesimal in a technical sense means it's a quantity it is a quantity that is smaller than all positive numbers, but not equal to 0. So right off the bat, that rules out the number having a decimal expansion. You can't have a decimal expansion if you're smaller than all decimals. And again, these are not real numbers. They are an idealized point of view. They are an idea that lives in my head, and maybe you can make some space in your head for them to live there too. Now, we can use the idea of change in these variables, change that is infinitely small. We can use this idea whether or not our variable is an independent variable or if our variable is dependent. So here I've written y in function notation. I say that y of x equals sine of x. But from the differential point of view, my dx is representing a small change in the variable x, and my dy is representing an infinitely small change in my variable y. So if these were numbers that I could compute, they aren't, and I can't. But if they did, if I lived in a much better world where these did actually exist, then I could calculate my slope, right? My slope is just rise over run. So my slope for the sine function should just be my differential in y divided by my differential in x. At this point, I don't know how to assign that an actual number, but it would be a useful thing if I could.